Welcome back to module 4, Python tutorial 4 of this course, time dependent quantum chemistry. In this module we have, in this tutorial we have learned how to represent a matrix and then how to get the eigenvalue eigenvectors, and Python has a particular way of presenting eigenvalues and eigenvector, and we have to collect that information specifically. So, we look at it how to collect it. Python will be clubbed every eigenvalue and eigenvectors in a particular arrangement, and if we want to collect it, the way it is presented here is that this particular eigenvalue is corresponding to the first column of this matrix, this eigenvalue matrix, V matrix, and the second eigenvalue corresponds to the column of this second column of this matrix. So, we will check it how to get that. We will first write down specifically, instead of printing E, we will just print E0, the first eigenvalue, and corresponding V, if we want to corresponding eigenvector, if we want to plot print, then it is going to be colon comma 0. So, entire column has to be printed. Similarly, there are two eigenvalues we have. So, second eigenvalue is going to be, it is going to be 1, because index starts from 0, and the corresponding eigenvector is going to be now 1. That is the way we can pull up the information specifically, and if we run this program, we get following results. Corresponding to the eigenvalue 3, I have this eigenvector 0.7, 0.7, and this is going to be the row vector, column vector actually. So, I will go back to the slide right now. So, corresponding to the eigenvalue 3, I have now this eigenvector, the right normalized eigenvector. Right normalized eigenvector is nothing but the a column matrix. Column matrix is represented by 0.7 by 0.7, and corresponding to this eigenvalue, I have another column matrix which is minus 0.7 and 0.7. So, these are the two matrices we have, the eigenvectors we have, and if we compare these two eigenvectors, we will see that the same results we have got. Basically, we represent, when we did analytically, we have got the eigenvectors as square root 1 by square root, which is nothing but the value which we have got here, and another eigenvector was minus 1 by square root of 2, 1 by square root of 2, and that is exactly what we have found here. So, numerically we get the same result. Only one point to be remembered here is that the way this array has been represented, it looks like a row matrix. This is just a visualization, that is the way Python will print. Python is printing like a row, does not mean that it is a row matrix, it is actually a column matrix. We have to remember that. So, it is just a visualization, and one can change the visualization by changing certain, by giving certain command in this construct. We will just skip that, because that details we do not need immediately, but we will remember that this is just a printing issue of Python. The Python will print it like this way, but it is actually this EV, this construct will give me only right normalized eigenvector, that we have to remember. It is going to be always right normalized eigenvector. Right normalized eigenvector, it is nothing but a column matrix. Like this. So, corresponding to a particular eigenvalue, how to get the eigenvector, that we have already found. And if we have this results, then one can actually go ahead and test. One can now test the properties of these eigenvectors. Properties such as we know that if I have eigenvectors, there are two eigenvectors if I have, then inner product with itself, because it is normalized, it should give me 1. Inner product with the other eigenvector, so it is going to be orthonormal. Each vector would be orthonormal. So, if I take the inner product with itself, it is going to be 1. So, both would be 1. This one also should be 1, but if I take the inner product with the other vector, it is going to be 0 because it is orthogonal to each other. So, let us prove that we have situations like this, and to get the inner product is a very simple way to get the inner product. Inner product can be used with this at the rate sign. This is the vectorial product. So, in general, scalar product is used by this star. So, A multiplied by B, this is the scalar product, but if I want to take vectorial product, it is going to be, the inner product is going to be A at the rate sign B or A. So, we will take a look at it whether these vectors which we have created already, they follow the properties which we are familiar with. They should be orthonormal. So, I will be able to take the inner product as follows. I have this eigenvector, and if I multiply this eigenvector vector product, inner product, so then I can also take the inner product for the other eigenvector, and I can take the between two eigenvectors. So, if we do that, then I get back following information. I will go back to the slide. I have the first inner product between these two eigenvector is giving me 1. It is close to 1. So, this is a numerical value, and it means that this vector is normalized. On the other hand, if I take the other vector inner product, that is also normalized, and if we take the inner product between two vectors, then what I get is 0, which means orthonormal. So, what we are getting is this EIG functionality is giving me orthonormal right eigenvectors corresponding to a particular eigenvalue. We have proved this one. We will move on, and we have already seen the general procedure to construct the matrix. Now, we will move to this tridiagonal matrix. Tridiagonal matrix is something which we will be dealing with in quantum mechanics very frequently, because the kinetic energy part adopts this tridiagonal form. So, if it is adopting tridiagonal form, we have to learn how to get that eigenvalue eigenvector of the tridiagonal matrix. Now, if you look at the tridiagonal matrix, something is very interesting to note. Its diagonal elements, all diagonal elements are actually 2. Then upper diagonal elements is -1, lower diagonal elements is also -1. So, instead of 3 by 3 matrix, if somebody is asking me to construct, let us say 3000 by 3000 matrix, 2-dimensional matrix, in that case I have to write down 2 2 2 in the diagonal form, -1 -1 like this way in the upper diagonal form, and then -1 -1 in the lower diagonal part also. And this needs to be written many times. So, previously what we have done, we have manually, once we have created the null matrix, we have manually entered the values of the each element. We have reassigned the values of each element manually. We can automate the process matrix construction by using a for loop, and that is exactly what we are going to learn. For a matrix of, let us say, 3 by 3 dimension or 2 by 2 dimension, we may not need a for loop. We can manually enter the re-enter the values of each element. But if you are constructing a large matrix, very large matrix, then for loop would be the only option, and one should make use of this automated option. So, we will look at it how to automate the process. The first step is, as usual, we will first create the 0 matrix, and that we will keep it as it is, 0 matrix, and in this case we will make 3 by 3 matrix, because our desired matrix dimension is 3 by 3. So, we will call it zeros 3 by 3, that is the way we will mention, and then instead of assigning manually, we will assign through automate the assignment process. So, we will write down as for I in a range functionality we will use. So, we will import this a range functionality. Previously, we have seen a range functionality can produce a list of elements. So, a range 3, this is something which we are using for the first time, and I will explain what does it mean by a range 3. Previously, I will go back to the slide. So, previously we have always used this a range functionality as a range functionality as start, then stop, then step. So, it will give me, it will, so if the a range functional, if I am giving this to be 1, then 4, then 1, it will create a list of element like 1, then 2, then 3, and it will stop at 3. Because the stop is not included in the list, in the sequence. That is the way a range functionality works, and that is the construct which we have used before. It is giving me the list of elements which I need. But there is another very frequently used construct for the a range functionality, and that is called a range. Just write down a range stop. So, what it does, if I do not use 3 input for the a range functionality, if I use only 1 input, it will be considered to be as stop input, and then by default it will consider 0, 1 like this, and then stop -1, because it will exclude stop and it will print up to stop -1. So, by default it is taking the step size to be 1, the step to be 1, and starting point to be 0. So, that is the default input it will take. So, a range functionality works with both constructs. One construct where we give 3 inputs together, where we can control where to start and where to stop and what is the step size. But if I use only a range functionality with only 1 input, that 1 input would be considered to be the stop input, and by default it will start from 0 and it will end at stop -1 value, because always it will exclude the stop value, and that is exactly what we have done here. If I say a range arrange 3, it means I am getting a list of following list 0, 1, 2 following list, and arrange 2 I will get list 0, 1, 2 will be excluded. So, these are the list I am getting, and this functionality we are going to use right now. So, we have for I in arrange 3, I have to specify now I comma I. So, what I am going to do right now, diagonal elements I am specifying, and I know that diagonal elements is going to be aii, that is 2 always. Next I am going to specify off diagonal, upper diagonal and lower diagonal elements. I in arrange, I am going to use 2, and then a I comma I plus 1 is going to be minus 1, a I plus 1 comma I, it is also going to be minus 1. So, upper diagonal elements will be expressed by I plus 1, lower diagonal elements will be expressed by I plus 1 I, and both values are 1. So, we will be able to get the matrix. We will do one thing, after construction we will just print the matrix to check what we have constructed. So, if we run the program, we get the desired matrix where diagonal elements are 2, upper diagonal elements are minus 1, lower diagonal elements is minus 1. And so, we have constructed the matrix which we want to do. So, what will happen in the first, we will go back to the slide right now. In the first loop, it will collect the value for a 0 0, that is going to be 2. Second loop, it is going to be 1 1, that is going to be 2, and third loop it will collect the value 2 2, that is going to be 2. So, I have first row first column, second row second column, third row third column. Third row third column is given by a2 2, which is the element 2. So, this is all about this iteration. For this iteration, for the first iteration, I will have a I value will be taken from arrange, and you look at this. For the first iteration, I have set the arrange to be 3, which means that I have only index value to be I value to be selected from 0 1 2 only. So, 3 values are selected, and these are the indices which you have selected from the arrange functionality. On the other hand, for the next one, I have only option 2 0 1, and that is why we will write down first one is 0, and then second one is going to be 1, that is going to be minus 1. So, what it does in the first loop, I am reassigning as minus 1. So, this is going to be the first row second column. First row second column is going to be this one, then second row first column is going to be this one. So, this 2 has been assigned. In the second iteration, this is the first iteration, second iteration I will have a next number is 1. So, it is going to be 1 2, that is going to be minus 1, and 2 1 is going to be minus 1. So, I have these values and these values, and then I do not have any other numbers. So, that is why the for loop will terminate and will go to the next command line. So, for loop will be running for 2 iterations here, and here for loop will be running for 3 iterations, and that is the way we are replacing, automating the construction of the this construction of this matrix. So, we have got back the Python representation of this matrix. Next, what we will do, we will just follow the the usual procedure to find out the eigenvalue eigenvectors of this matrix. We will just write down E comma V equals, the first one would be, the first option is going to be eigenvalue, second option is going to be eigenvector, which can be represented, and then A. So, if we do that, and then if we print print E, so this is Python will be printing on its own way. One can extract each eigenvalue and eigenvector following the constructs I have already shown. So, if I print these two, then what I get is that it has 3 eigenvalues. We will go back to the previous to the slides right now. So, I have now this is one eigenvector, eigenvalue, then another eigenvalue, and then another eigenvalue. So, there are 2 eigenvalues I have. One is this one. So, each one having this complex notation, I do not need this complex notation, each one is 0. That is why this is one eigenvalue, this is another eigenvalue, and this is another eigenvalue. There are 3 eigenvalues I have, and corresponding eigenvectors are following. I have to construct, this is one eigenvector, then this is right eigenvector corresponding to this, and corresponding to this is another eigenvector. So, there are 3 eigenvectors I have already found in the and these will be all in grid representation. So, we can directly calculate the eigenvalues and eigenvectors of a tridiagonal matrix, but this is not the procedure which I am showing, the direct procedure where I am using this that I am making use of the entire matrix. This direct procedure can be useful for the lower dimension, like let us say 3 by 3 matrix I have. In that case it can be very quick, but when we have very large, very large tridiagonal matrix, and if you are dealing with very large trigonal matrix, one can go over this the elemental map of this matrix. If we carefully go over the elemental map, we see that all the elements are actually 0, and only I have this for the tridiagonal matrix. I have the diagonal matrix elements which are non-zero, and upper and lower diagonal elements are non-zero. So, there are procedure which one can follow to represent the different storage form. One can use a different storage form for this kind of large trigonal matrix to reduce the computational time. So, if you are dealing with very large tridiagonal matrix, it is better not to directly use this matrix and find out the eigenvalue and eigenvector with the help of this construct. We should not do that. We should use some other technique which would be more computationally time effective if we perform in a different way. So, we will present it how to deal with very large tridiagonal matrix, and we will prove that if we directly do that calculations, instead of doing direct calculation, if we do it in a band storage form, then the computation would be much more efficient and computational time can be extraordinarily reduced. So, in quantum mechanics, we often work with very large Hermitian matrix of tridiagonal form, which is shown here, and a generic structure of the tridiagonal matrix shown here. A square matrix possessing non-zero elements only in the main diagonal is called a diagonal matrix. So, if I have a matrix where only diagonal elements having non-zero values, remaining part is 0, then it is called diagonal matrix. The main diagonal of a matrix consists of elements that lie on the diagonal that run from top left to the bottom right. A tridiagonal matrix, which is presented here, has non-zero elements on the main diagonal. This is the main diagonal, and on the upper diagonal, this is upper diagonal and this is lower diagonal part, and these values would be non-zero in a tridiagonal matrix. So, in a tridiagonal matrix is also called a band diagonal matrix, because it is only non-zero element are confined to a diagonal band. So, one can think about a band like this, and all non-zero elements have been confined within this band, and that is why it is called also band diagonal matrix. Now, in module 4, we have realized that the defining condition of a Hermitian matrix, this is an Hermitian matrix, and defining condition of a Hermitian matrix is that it is self-adjoint. So, if it is an Hermitian matrix, it has to be self-adjoint, and self-adjoint, what does it mean? Aij is going to be Aj star, and due to this symmetry, because it is self-adjoint, due to this symmetry of Hermitian matrix, a tridiagonal matrix, n by n matrix, can be stored as 2 by n band storage form. So, this is called band storage form. So, the point I am trying to make here is that instead of dealing with very large tridiagonal matrix, one can store the entire tridiagonal matrix in its band storage form. And if we do that, then one can see that the actual matrix was n by n, let us say 3000 by 3000, the big matrix, that can be stored as 2 by n, which is 2 by 3000, let us say. So, the memory which will be used to store the matrix can be reduced significantly if we use this band storage form of the tridiagonal matrix. There are two ways one can store the tridiagonal matrix in the band storage form. One is called the upper diagonal elements, with the help of upper diagonal elements. Upper diagonal elements, so we know that this is diagonal element and this part is upper diagonal element. So, with the help of only upper diagonal element I can store it, and the way I can store it is following. I have 0, then so first would be 0 and then this upper diagonal elements, and then the diagonal elements. On the contrary, one can also store with the help of lower diagonal elements, and in that case it is going to be the diagonal elements first, and then in the second row we will have the lower diagonal elements with 0 in the end. So, these are the two different representations of band storage form. So, what we get is that we are actually storing the very large Hermitian tridiagonal matrix in the band storage form to reduce the memory consumption for the entire when you are dealing with the matrix. And if we do that, this band storage form, then psi pi linear algebra, the submodule gives me one very efficient functionality to calculate the eigenvector and eigenvalues for this kind of matrix, if it is stored in the band storage form. So, and with the help of this, so it instead of only EIG within bracket, I have to use now underscore then banded then bracket. So what will the bottom line of the entire discussion is that if I have a very large Hermitian tridiagonal matrix, first thing I should do to reduce the memory consumption and to make the computation effective or faster, we have to convert this matrix form, this large matrix to one of the band storage forms, either upper diagonal with the help of upper diagonal elements or with the help of lower diagonal elements. Their structures are different, but one can convert it. The moment we convert it, we get this 2 by n matrix, and then this new matrix I will name it, let us say B. So, this was A, I will call it B, and then I can find out the eigenvalue and eigenvector using this construct EIG underscore banded B. So, we will take a look at it, how to do that. We will move to the laptop right now, and we have already constructed the tridiagonal matrix, and this tridiagonal matrix we have constructed. Now, we will construct two cross 3 band storage form. So, we have to now reconstruct the band storage form, and for that what we will do, we will use upper diagonal elements. So, for that what we need to do, we have to start with a null matrix of 2 by 3 dimension. So, remaining part, this part is not of use, we will just keep it as it is. So, this part is to show conventionally how to prepare the large matrix, and then directly how to get the eigenvalues and eigenvector. We are not following that procedure. So, these entire steps will be obsolete right now. We are following another steps. The steps is that by looking at the matrix which we are going to prepare, it is clear that it is a tridiagonal Hermitian matrix, and that is why we can store it in a band storage form. And in order to store the band storage form, first we have to prepare the null matrix. So, we will prepare zeros 2 by 3, and we have named the null matrix as A band up. Up we are showing because we are going to use the upper diagonal elements, and then we will automate the procedure for I in a range 2 this matrix, this array values has to be specified, and this is going to be 0 comma first row and I plus 1. This is going to be minus 1.0, and for I in a range 3, I have to now reassign the elements. It is going to be first row and this, and that value is going to be 2.0. What we will do, we will now print to see what we are constructing. So, we have constructed the band storage form, and now we run the program. Okay. So, what we have done, we are commanding to print the normal form of the tridiagonal matrix. So, that has been printed here, and then with the help of the upper diagonal elements we have printed this. So, that is the band storage form with the help of upper diagonal elements. So, take a look at it. Let us go back to the previous slide. So, we have shown in the slides. So, what we see here is that if we use the upper diagonal elements, here we are using upper diagonal elements, the first element, the element at the first row first column is going to be 0, and then remaining part is going to be remaining, the each element in the different column of the same row, it is going to be -1, and that is exactly what we have commanded here. If you go back to the laptop, we will see that for this iteration, the first iteration, for the first loop, I have commanded that for the 0th row, which index 0 means it is a first row. For the first row and second column and onwards, first row, second column, first row, third column, first row, fourth column, like this way, all is going to be -1. And how far it should go? It should go up to arrange 2, which means that 2 will be excluded. So, I have only 0 and 1. So, it should go up to 1 and 2. So, 2 elements I have, -1, -1. On the other hand, for the next for loop, I have set the row to be 1, which means the second row, and for entire column I have to use 2 values, and I get this band storage form. So, this is exactly the band storage form with the help of upper diagonal elements. Once we have that band storage form with the upper diagonal elements, one can actually calculate the eigenvalues and eigenvectors. So, I will put this to be, we will do both. Directly we can calculate the eigenvalues of the entire matrix which is here, or one can also calculate the eigenvalue eigenvector of the band storage form corresponding to this, the matrix A. This is the band storage form, and in that case I have to use eigenbanded. This is the construct. So, I have to also import the same functionality from SciPy linear algebra submodule. So, if we run this program, and we have to print it. So, print E, print V, here also we have to print, we will name different, we will make it E1, V1, and this one as E2, V2. So, this print would be 1, 1, and this is going to be E2 and print V2. So, if we do that, what we get is that we get the same results actually. If we run, if we try to calculate directly with the help of entire matrix, and if we run the calculations with the band storage form, we see that the same results we are getting. In the band storage form, the values are 0.58, then second one is 0.2, third one is 3 point something, and that is exactly what we get, 0.5, 2 and 3.4. These are the three eigenvectors we get. On the other hand, corresponding to 3.4, this eigenvalue, I have this eigenvector -5, 7, -5, and what I get is 5, -7, 5. So, this part, this negative part is coming into the fact that you have this, if you multiply each element by -1, it is going to give you these values. So, they are the same eigenvector. On the other hand, for corresponding to 2, we have now -7, 4 and 7. And here I have 0.5. So, corresponding to 0.5, I have then 5, 7, 5. So, I have -5, -7, -5. So, they are representing the same eigenvectors which I have calculated through the band storage form. So, now one may want to use another convention. One can use the lower band for the band storage form. So, I will write down lower, and if it is lower, then these values would be 0, first 0 and then this is going to be 1 and this is going to be 2, and second one is the 1i and that is going to be -1, and this one going to be 2 and this is going to be 3. Now one can, this is going to be lower, and if we now print this entire band storage form, and here also we print A, what we see here, now we are actually using the lower diagonal matrix. So, if we look at, if we go back to the slides, we see that if we are using the lower diagonal elements, then that is the band storage form we use. Then the diagonal elements comes in the first row and second row will be occupying the lower diagonal elements. The last value would be 0, and that is exactly what is going on here. Last value is 0. So, we are getting the getting back the this matrix band storage form, and one can now calculate the eigenvalues and eigenvectors by this But in this case, because we are using lower diagonal elements, we have to, by default it is taking the upper diagonal elements, but if I specifically want to use lower diagonal elements, then I have to make lower to be true, then it can calculate, otherwise it will not be able to calculate it. And then you have to print it, print E, print V, so it's giving me the same result 0.5, 2, 3.4, these are the eigenvalues, and so I get back the same eigenvalues. It depends on what kind of storage procedure we are following, and if we have a particular procedure to store, we will just use it. So if I do not use this lower equals true, then I will have some value, but these values are wrong, because now it is not, it does not know whether I have used a lower band storage form. It is accepting that I am using upper band storage form, and that is why they have taken it like this way. So it is going to be wrong, because by default it is going to be upper band storage form. So always we have to use this lower equals true if we are storing it in terms of lower diagonal elements. Then I get the values 0.5 to 3.4. That is exactly what we had previously, 0.5 to 3.4. One more point to mention here is that this lower equals true, this is the Boolean value. So it will always start with true like this, or false with a capital letter, but this lower is the input or the argument that is going to be the small letter. So we should remember this one when you are employing this. So we have come to end of this Python tutorial, where we have learned how to represent a matrix, how to represent a tridiagonal matrix. Kinetic energy matrix in grid representation is actually a tridiagonal matrix, Hermitian tridiagonal matrix. And when you are dealing with a very large tridiagonal matrix, one can use this one of the band storage forms, and once you represent in one of the band storage form, Python linear algebra submodule provides a particular functionality to get the eigenvalue and eigenvectors from this band storage form. We will meet again in next tutorial and modules.